structure. But okay, so maybe this part of argument I'll go over. So A is a linear map from V to V, and V is a Q module. It's a Q vector space and hence a Q module. So it defines V is a QX module such that X dot V is equal to AV. And B is a map from V to V, which is Q linear, because B is also a linear map of vector spaces. So the question is it QX linear? So since V is a QX module, you can ask whether this map B is QX linear. So what does that mean? I.e. B of some fx dot V is this equal? So QX linear, I mean additive part is okay. So QX only QX linear only has to we only have to check whether scalar multiplication is okay. Is the same as fx dot bv. Yeah. So this equality one has to check. But what is this? So how does so we know what this QX module structure is? Yeah. So fx dot v, it happens to be fa times v. Yeah. This was the description in our result. Yeah. So this is same as so this is b fa v. Yeah. Left hand side is this, and right you want to write it as FABV. So this will be equal to FABV if AB equals B. Yeah, because you are going to change A and B many times, yeah, depending upon what the degree of the polynomial is. Okay, so this tells you that that this is this map is QX linear if AB equals BA, and which is the case in part A. So from here you can just say that this implies V is now take R to be QX. So then V is Rx, but I don't want to confuse with the variable, so I'll say Ry module with so V is Ry module with y dot V equals this linear map B, BV for all V in V. Okay. And that's it. So so Ry, but Ry is QXY. So now you have V is an RXY module where X dot V is already AV and Y dot V is BV. Yeah, so this is how you can construct give a QXY module structure. So then you don't have to verify module axioms because you are quoting results from the class. Okay. Any other question? Okay, so if there are no questions, let me.
Here, fxy dot v is defined only if AB is equal to BA.
Fxy dot v you can define this way. So fxy is some polynomial which you can in qxy, which you can always write it this way, and then you define it this way.
Yeah, it is defined only if AB is equal to BA. Otherwise, if we write y power j times x power I, then it will be b power j times a power I, and it will not be equal. I mean.
Yeah, but y power j times x power I, you can write it as x power I times y power j. So
yes, that's what I'm saying.
Yeah, so that's what I'm saying. So any polynomial you can uniquely write it this way, and that's why it's important to define it properly. What the map is.
So we define it as the product is defined as a power I times b power j only.
Yeah. So any polynomial you can uniquely write it this way: aij x power I y power j. Or you can, if you want to be very pedantic, you can say that it's a polynomial in y with coefficients in qx, and then you are writing it this way. Okay. So you can always define this thing. You don't really need AB equals BA to define this this
Okay.
scalar multiplication. Okay.
Okay.
Yeah. So even if something is given like this, you just write it this way, and then this is what the definition is. Okay, so let's yeah. So those who would see the record, so I'll share the quiz this page as well, so that people can who missed the lecture can see this part. I mean, I guess it's fairly detailed. Okay, so now let's get to the lesson. So. Okay. Yeah. Noetherian modules. Okay, so today we'll talk about Noetherian modules. So so given an R module, so we had already talked about Noetherian rings. So Noetherian modules is a slight variant of it. It's some property of modules instead of rings, and it's a useful property which will be needed to prove structure theorem and so on. Yeah. So when Noetherian rings, these modules are well understood, but over non-Noetherian rings, this is slightly more complicated. Yeah, but it has nice properties. Yeah, so so that's why so this class of modules behave well. So that's why we are looking at these kind of modules. Yeah. So what is the definition? So let R be a ring, M be an R module, then the following are equivalent. Every R submodule of M is finitely generated. Yeah. So so like in Noetherian ring, we wanted every ideal should be finitely generated. Here it's like every R submodule of M should be finitely generated. Every increasing chain of R submodules of M is eventually constant, which means precisely this, that if M0 contained in M1 contained in Mn are R submodules of M, then there exists N such that Mn equals M sub N for all N greater than N. And number 3, every non-empty collection omega of R submodules of M has a maximal element. An R module M satisfying the above equivalent condition is called a Noetherian module. Yeah? So these three are equivalent, and Noetherian module is something which satisfy one or and hence all of these equivalent conditions. So why they are equivalent? The proof is exactly the same, more or less the same, like in Noetherian rings. So I'll just go over it a little fast. So for instance, one implies 2. So you are assuming every submodule of M is finitely generated. You want to say that if every increase in chain is eventually constant. Yeah? So so suppose you are given an increasing chain of R modules, you just take their union. Yeah. Then first observation is MS is an R submodule of M. So because if you take any two elements in MS, then it has to lie in MI and MJ. So you take whichever is bigger, and then their sum is going to be in there, and scalar multiplication will also be in there. Yeah, so MS is an R submodule, and of course the union is contained in it because each of them is contained in it. Yeah, so MS is an R submodule, but by one that means that MS is finitely generated, and say by M1 to ML, then and then these M1 to ML has to be in one of these MIs. So you take n such that so there will be a capital N such that M sub capital N will contain all these M1 to ML. And then of course MS is going to be equal to M1. Yeah, so that is the place where it stabilizes. Okay, and 2 implies 3 is also straightforward. So yeah, since omega is non-empty, you can always find one element. So we want to show that every non-empty collection of R module has a maximal element. So so omega is non-empty, then we can find M0. And and the lack of maximal element in omega will allow us to build a chain of strictly increasing sequence of R modules, R submodules, right? Because if M0 is not maximal, then there exists some M1 in omega which is strictly bigger than M0. Yeah, and then you take that M1, and which will again be a submodule, R submodule of M. And now if M1 is not maximal, you can find another R submodule of M which is strictly bigger than M1, and so on. Yeah, so that is what we get, and that will contradict 2. Yeah, so 2 implies 3 is done. Yeah. And for 3 implies 1, so we assume that every non-empty collection omega of R submodules of M has a maximal element. Then we want to prove that every R submodule of M is finitely generated. Yeah. So take yeah. So what I'm showing here is actually M1 M is finitely generated. So so that is not what I wanted to do. Yeah. So maybe I'll correct this argument. So take so let N be a submodule of M. Let M0 be a submodule of M. We want to show M0 is finitely generated. Yeah. So now take M1 in M0. Yeah. Then you declare. So I'm going to use omega. I'm going to cook up omega. Yeah. So then you take M1 to be the module generated by RM1. Then M1, of course, is a submodule of M0 and hence a submodule of M, a submodule of M. Yeah. And M2, then M2 you take, so if M0 minus M1 is non-empty, then you take M2 in there. If M0 minus M1 is is empty, then that tells you that M0 is generated by just one element. And M2 you declare it to be RM1 plus RM2, and so on. Yeah. So you continue this, then you take M3 from M0 minus M2 if it is non-empty. If it is empty, then of course M0 is 2 generated. So to construct omega, and you continue this way to construct omega, which is mi I greater equal 1, let's say. And then omega is a collection of construct omega, a collection is a collection of R submodules of M0. So they are all submodules of M0 and hence R submodules of M without a maximal element if M is not finitely generated. So if M is not finitely generated, this is actually a strictly increasing chain of modules, submodules of M. Yeah, and hence it won't have a maximal element. Okay, so it will contradict 3. It will contradict 2 as well, but it will, in particular, it will contradict 3. Okay. So that proves 3 implies 1. Any questions? Okay, so if there are no questions, let me so what are some examples of Noetherian modules? So if so first observation, if R is a Noetherian ring, then R as an R module is Noetherian. Yeah, because any submod, so this is since every submodule of R is an ideal, and then R ideal, then if R is Noetherian, ideal is finitely generated, so it satisfies 1. So every submodule is finitely generated. So in fact, this is if and only if. So R is a R as an R module is Noetherian. Is Noetherian if and only if R is a Noetherian ring. So in fact, R as an R module is Noetherian if and only if R is a Noetherian ring. Because if R is not a Noetherian ring, that means you can find an ideal which is not finitely generated. But that ideal is going to be a submodule of R, which won't be finitely generated as an R module. Okay. And now, so if you want, so if so maybe R is Z, then we know that R modules are same as abelian groups. So what? So every so R is Z, then every finitely generated R module is Noetherian. Okay, so in fact, but of course, any finite. So if the module itself is finite, so this we will see more generally. So if R is a Noetherian ring and M is a finitely generated R module, then we will show that that R is indeed, and then M is indeed Noetherian. But if you consider, so this, so maybe if you know structure theorem for abelian groups, you know any finitely generated Z module is going to be a finitely generated abelian group, and that so maybe by structure theorem. I don't know if you have seen it, but if you haven't, we will prove it for general PID. So you'll see it anyway. But anyway, so this is a sort of circular argument if you haven't directly seen it. But this looks like Z power R plus Z mod plus some finite. So maybe you don't need the structure theorem in the full thing. Plus M, where M is a finite abelian group. Yeah, so if you take any subgroup of this, then it is again going to be of something similar form. Yeah, so there is some work to it, but So M part won't be a problem because any finite abelian group is of course finitely generated. You can take all its elements, for instance, yeah, or any subgroup of finite abelian group is finite abelian. Yeah, so maybe one remark is that R a ring, M an R module such that M is finite as a set, then M is Noetherian. Okay. So what will be an example of a non-Noetherian module? So if R is a if R is non-Noetherian ring, then it's easier, right? You just take R to be R to be that module itself. But if if R is equal to Z, then something which is not finitely generated is not going to be. So maybe Q is not Noetherian because Q as a Z module is Noetherian Z module. Or you can take infinite copies of Z. So infinite copies of Z. So product of Z, the scalar multiplication is component wise, so that makes this into a Z module, and this is not going to be Noetherian. Or you can take infinite direct sum as well. So these are going to be are non-Noetherian. Now one observation, which is a trivial observation, is that if M is a Noetherian R module, then any R submodule of M is Noetherian. Okay, so finitely generated R modules are close to Noetherian. So it has to, I mean, for R module to be Noetherian, it better be finitely generated, right? Because you want to say that every submodule is finitely generated. In particular, the module itself should be finite. But a finitely generated R module may have submodules which are not finitely generated. So this property being finitely generated is not as nice as being Noetherian. So Noetherian has this property that every submodule is also Noetherian, and this for this you can just use equivalent condition 1, because if N is some submodule, then of course if M is Noetherian, N is some submodule, and A is a submodule of, and K is some submodule of N, then K is also a submodule of M, so K is finitely generated. So that tells you that every submodule of N is also finitely generated, and hence N is Noetherian. Yeah, so M is closed under Noetherian. So Noetherian property is closed under taking submodules. So another thing which is nice about the second thing is closed under quotient as well. Yeah, but that's true about finitely generated modules. Yeah, so note that if M is a finitely generated R module and N is an R submodule of M, then M mod N is finitely generated R module, right? Because I'll just lay down an argument. So let M be generated by Rm1 to Rmn. So generated by literal n elements. Then, of course, the images will generate it. So M mod n is going to be generated by is R M1 bar X Rmn bar. Yeah. So if you take their images, they will generate any element in M is a linear combination of M1 to Mn. And then any element in M mod n is going to be image of some element there, and that you can write it as a linear combination of M1 to Mn, and their images will be it will be the same linear combination of their images of M1 to Mn quotient. Okay. So quotient of a finitely generated R module is finitely generated, and that tells us that so as a consequence you get that if M is a Noetherian R module, then M mod n is Noetherian R module, where n is a submodule. Why? Because if you take a submodule of M mod n, that means it's I don't know, so maybe K is maybe K bar is contained in M mod n is a submodule. Then K bar equals K mod n for some. So this I mentioned last maybe a couple lectures ago. Submodule for some submodule K of M containing n. So, since M is Noetherian, K is finitely generated, and hence K bar is finitely generated. So every submodule of M mod n is finitely generated. Okay, so M a Noetherian R module implies M mod n is also Noetherian. So Noetherian is closed under taking quotients and taking submodules. Now for Noetherian rings, finitely generated and Noetherian are same. Yeah. So of course, if M is Noetherian, then it is automatically finitely generated. The converse is the difficult part. Yeah. So the proposition is R is a Noetherian ring and M is a finitely generated R module, then M is a Noetherian R module. So we'll see a proof of this, but maybe let's take a break. So maybe we'll reconvene at 12:05 and complete the proof of this thing. So we'll see a proof of this thing. So R Noetherian ring, M a finitely generated R module, then M is a Noetherian R module. Yeah. So what does it mean to say M is finitely generated? So let M1 to Mn be in M such that M equals R M1 plus R. Yeah. So M is finitely generated. Then what it also means is that you can give so you can realize M as a quotient of Rn. Yeah. So let phi from Rn to M be the map sending E1 EI to MI. Yeah. So I should actually say EI will go to MI, and then you can extend linearly or more precisely. So I'll give you what the map is explicitly. So A1 to AN will go to summation AI MI. Yeah, I equals 1 to N. Okay, for AI is in R. Okay, so one you can so by the fact that M is finitely generated, this tells you that phi is surjective. I mean, the map is obviously well defined because I'm defining it in terms of this n tuple of elements in R. Phi is surjective, and one has to check that it is R linear. Yeah, surjective, and phi of so to check it's R linear and R linear. So surjective is clear. So and for R linear, you just make this observation. So let surjective is okay, and let A belongs to R, and there be two n tuples. So A. So maybe let's call this scalar as x. Yeah, x belongs to R, and A B be element of Rn. Then phi of x A plus B. We want to show that the same as x times phi A plus phi B. But what is phi of xa plus b? So what is xa plus b is x a1 plus b1. So this is how the module structure is. X times a is just x a1 comma x a2 comma x an, and then if you add b, then it's component-wise addition. So if you combine these two, then you get this thing, x an plus bn. So this is the n tuple you get, and phi of this n tuple is summation x a1 ai plus bi times mi. I equals 1 to n by definition of phi. And now we use the fact that M is an R module, and X, AI, BI are all elements of R. So this is same as summation I equals 1 to N X, AI, MI plus BI, MI. Yeah, I can write it this way. And this is same as summation I equals, okay, I should have simplified this. So x, I can pull it out now. X times AI mi plus summation I equals 1 to n bi mi. But summation ai mi is precisely the image of phi a, of a under phi. So this is phi a, so x times phi a plus phi b, yeah, by definition. So this shows that phi is indeed R linear. So this is a epimorphic. This is a surjective map, and hence so M is so M you can write it as so this implies M is isomorphic to Rn mod kernel phi by first isomorphism theorem. So if we so maybe I should write it first. Yeah. So by this observation, which we made here, where was that observation? Yeah. So our Noetherian R module implies M mod n is Noetherian. It's enough to show that Rn is Noetherian. So once we have that R power n is Noetherian, M being isomorphic to Rn mod kernel phi is automatically going to be Noetherian. Yeah. So upshot of this thing is hence enough to show R power n is Noetherian R module for all n greater equal 1. Yeah. So that is what we will prove, that R power n is Noetherian for all n. And this we can prove by induction. So proof by induction. By induction. And of course, n equals 1. N equals 1 is okay since R is Noetherian. Since R is Noetherian ring. Since R is Noetherian ring. Okay. So that was this observation that if R is a Noetherian ring, then R as an R module is Noetherian. Yeah. So okay. So n equals 1 is okay, and assume this computer. Okay. Yeah. So okay. So since R is Noetherian, n equals 1 case is done. Now assume this is true for a general n. So assume R n minus 1 is a Noetherian R module for n greater equal 1 for some n greater equal 1. Then we want to show that n greater equal 2 maybe. N greater equal 2. Then we want to show that is true for n equal Rn as well. Yeah. So what is Rn? Rn we can write it as Rn minus 1 cross R. Yeah. Or dx sum R. So let's think of it as product, yeah, and tuples. So let's think of it. So so Rn is Rn minus 1 cross R. Want to prove, want to show every submodule of Rn is finitely generated. Yeah, so this is what we want to do. Yeah? And then the proof will, assuming that Rn minus 1 is Noetherian R module, and of course R is also Noetherian R module, since R is Noetherian. So let M contained in Rn be a submodule, R submodule. Okay. Then we can cook up. So I want to find finitely many elements in M which will generate M. So what I'll do is I'll project M onto these onto one factor, and maybe think of something, some elements in M which come from the second factor. Yeah. So note that Rn minus 1, we can identify it as a submodule of Rn. Yeah. So maybe so Rn minus 1 as a submodule. So what is this description? Obtained in Rn as A1 to An minus 1, comma 0. AI is in R. So this is the submodule I'm thinking of. This is how I think of Rn minus 1 as a submodule of Rn. Yeah. Is an R submodule of Rn. Yeah. So and we want one map from Rn to R. So Rn to R, we consider this map, let's call this pi, projection map. So A1 to An goes to An. Yeah. So maybe yeah. So what is the kernel of pi? So this of course is R linear. Yeah. Projection onto the last factor is R linear map. And what is the kernel of pi? This is precisely this Rn minus 1, which is this guy A1 to An minus 1. So we'll use these two, this kernel of so this projection and this kernel to cook up our generators. Yeah. So of course, M being a submodule of Rn, M intersection kernel pi is contained in Rn minus 1. Yeah, is a R submodule of Rn minus 1. It's an R submodule of M and Rn minus 1 both. Yeah, it's a submodule with the same scalar multiplication, and it's a subset of both M and Rn minus 1. Yeah. So let's call this. Let's just give this a name. So maybe call it M1. And since Rn minus 1 is Noetherian, M1 is finitely generated. M1 is finitely generated since Rn minus 1 is Noetherian. Okay. So maybe we fix some less set of generators. So say by maybe let's call it x1 to xk. Yeah, the k generators. And declare M2 to be image of pi of M. M is a submodule of Rn, and pi is a map from Rn to R. So you look at the image of this submodule M. So it's again going to be M2 is a submodule of R, and so in fact M2 is an ideal. Yes, okay. Hence, and R is Noetherian. Hence, M2 is also finitely generated R module, say by another set of elements y1 to yl. Yeah, makes sense. So what I'm trying to do is I'm considering part of it in Rn minus 1 by taking the intersection of M with Rn minus 1, the first n minus 1 factor, and declaring the last factor to be 0. And then I'm considering another module which is image of M in R, which I call M2, and that also is finitely generated. Yeah. So now I'll use these two generating set to generate M. So of course x1 to xk is already this is contained in M. So I don't have to do. But y1 to yl are not elements of M. They are elements of M2, which is a quotient of. So what I'll do is pick one element of M, elements of M which maps to y1 to yl. Yeah, and then we'll claim that this x1 to xk together with these new elements will generate M. Yeah. So let z1 to let zi in m1, no, not m1, m be such that pi to zi equals yi for I between 1 and L. Yeah. So we can find such, so point is M2 is the image of not pi to pi. Yeah. There is no pi 1, so there is no need of pi 2. So second projection, yeah, but we're calling it pi. So pi of zi is equal to, so we can find such a zi because M2 is precisely pi of M. Yeah? So so pi is surjective onto M2. From pi restricted to M is surjective onto M2. Yeah? So the claim is, can go to the next page. So the claim is x1 to xk, z1 to zl, generate. Yeah. So we just follow this algorithm. Yeah. So this, this recipe essentially. So this is straightforward. So let x be some element of M. Then pi x. If you look at pi x will be an element of M2. Yeah, belongs to M2. So and M2 is generated by y1 to yl. So this implies pi x is going to be summation ai yi I equals 1 to L for some ai's in R. So that's okay, but we want x to be generated by z1 to zl and x1 to xl. So what we can get is this. So this implies that pi x equals summation I equals 1 to L ai, but yi is same as pi zi. Yeah, pi zi, which implies pi of x minus summation. So pi is a linear map, so I can do this. I equals 1 to L. Pi of this is 0. Yeah. So what it tells us is that this this guy x minus ai zi, sorry, x minus summation summation ai zi I equals 1 to L is in kernel of pi. Yeah, because it maps to 0. And note that x is an element of M, and zi's are also elements of M. So this this expression, everything is and ai's are elements of R. So an element of M and minus an element of M is again in M. So it's not just in kernel pi; it's also in M. Yeah. So it's in the intersection, and that precisely is M1. Yeah. And M1 was finitely generated, so that's it. So this implies x minus summation I equals 1 to L ai zi. We can write it as summation bi bj, let's say xj, j equals 1 to k, because xj is generate M1, yeah, for some bj Vj in R, j between 1 and k. So this implies x equals summation ai zi plus summation bj xj I equals 1 to L and j equals 1 to k. Okay, so that that completes the proof. Sorry, something.
Can we say anything in general about the submodules of Rn?
Submodules of Rn. Yeah, so meaning when R is not Noetherian. In general means R is not Noetherian, or what are you trying to say?
No, I mean, can we give any? No, it's not about deciding this Noetherian or not. I'm saying that can we give any nice description of the submodules of Rn, like we did for ideals of?
Oh, whether I see. So whether some, yeah. So not really. I mean, it can be very crazy. Yeah. So so in nice cases, you can say it's finitely generated if R is Noetherian, but in general it could be very crazy and yeah. So you can't say much about it, and so number of generators, etc. Also you can't control in some sense. So it just for R itself, you can see if you take a complicated ring, the ideals are fairly complicated. Yeah. So there is no reasonable description.
Thank you, sir.
Yeah.
Excuse me, sir.
Yes.
So can we generalize this proof a bit, the latter part of the proof, to say that if P is Noetherian and Q by P is Noetherian, then Q is Noetherian?
If P is Noetherian and P by Q is Noetherian.
Q by P, sir.
If P is Noetherian and Q by P is Noetherian,
then Q is Noetherian.
Then Q is Noetherian. Yeah, this should be okay. Yeah, so maybe you can. Yeah. So this argument you can generalize to say that yes, if the submodule is Noetherian and the quotient is let me just think. Yeah, this looks okay. This is the argument basically, right?
Yes,
Yeah,
sir.
so I
It's
think
more or less similar.
yeah, so it's the same argument. Yeah, so you can use the same argument to say that.
Yes, sir. Thank you, sir.
Yeah, you're welcome. Okay, so this is all for today. So if you have questions, you can ask me in another minute. And if no, then we'll disperse.